Good evening. Welcome in RNQ Isino classes, block number 3, unit 3, uncertainty principle 3.1 introduction. This unit takes up one of the fundamental principles from quantum mechanics. It also studies the confusion and challenges created by it. Finally, it studies some of the implications of this history. 3.2 simple definitions of uncertainty principle. Finally, study some of the implications of this history. 3.2 simple definitions of uncertainty principle. The more preciously the positions are determined, less preciously the momentum is known. This is the simplest statement of the uncertainty principle in quantum mechanics. The positions and momentum of a particle can be simultaneously measured with arbitrarily high precision. There is a minimum for the product of the uncertainties of these two measurements. There is likewise a minimum for the product of the uncertainties of the energy and time. This is not a statement about the inaccuracy of measurement instruments nor reflections on the quality of experimental methods. It arises from the web properties inherent in the quantum mechanical descriptions of nature. Even with perfect instruments and technique, the uncertainty is inherent in the nature of things. Harrisburg formulated it in 1927. Thus, the more precisely the positions is determined, the less precisely the momentum is known in the instant, and vice versa. This is a succinct statement of the uncertainty relation between the positions and the momentum mass time velocity of a subatomic particle such as an electron. It asserts that the positions and the velocity of an object can both be measured exactly at the same time. Even in theory, the very concept of exact position and the exact velocity together in fact have no meaning in nature because of the scientific and philosophical implications of the seemingly harmless sound uncertainty relations. Physics speak of an uncertainty principle which is often called more descriptively the principles of indeterminacy. 3.3 beyond strong objectivity. Classical physics was caught simply completely off guard. This discovery of the uncertainty principle. Ordinary experience provides no clue of this principle. It is easy to measure both the positions and the velocity of, say, an automobile because the uncertainties implied by these principles for ordinary objects are too small to be observed. The complete rule stipulates that the product of the uncertainties in positions and velocity is equal to or greater than a teeny physical constant only for the exceedingly small masses of atoms and subatomic particles. Does the product of the uncertainties become significant? Oregon 2011. Any attempt to measure precisely the velocity of a subatomic particle such as an electron will knock it about in an unpredictable way, so that a simultaneously measurement of its positions has no validity. This result has nothing to do with inadequacies in the measuring instruments, the technique, or the observer. It arises out of the intimate connections in nature between particles and waves in the realm of subatomic dimensions. Every particle has a wave associated with it. Each particle actually exhibits a wave-like behavior. The particle is most likely to be found in those places where the undulations of the behave greatest or most intense. The more intense the undulations of the associated wave become, however, the more ill-defined becomes the wavelength, which is in turn determines the momentum of the particle. So, a strictly localized wave has a indeterminate wavelength. Its associated particle will having a definite positions has no certain velocity. A particle having a well-defined wavelength, on the other hand, is separate out. The associated particle will having a rather precise velocity, maybe almost anywhere a momentum preciously, but then its position is unknown. Notice that this is not the measurement problem. In another form, the combinations of positions, energy, momentum, and time are actually undefined for a quantum particle until a measurement is made. Then the wave function collapse. Also notice that the uncertainty principle is important to macroscopic objects, since planets constant H is also small 10 raised to 3. For example, the uncertainty in position of a thrown baseball is 10 millimeters or 2011. The depth of the uncertainty principle is realized when we ask the question, is our knowledge of reality unlimited? The answer is no, because the uncertainty principle states that theories is built in uncertainty, indeterminacy, unpredictably to nature. The field of quantum mechanics concerns to descriptions of phenomena on small scales, where classical physics breaks down. The biggest difference between the classical and microscopic realm is that the quantum world can be not be perceived directly, but rather through the use of instruments. And key assumption to an quantum physics is that quantum mechanical principles must reduce to Newtonian principles at the microscopic level. There is a continuity between quantum and Newtonian mechanics. Quantum mechanics was capable of bringing order to the uncertainty of the microscopic world by treatment of the wave function with new mathematics. Key to this idea was the fact that relative probabilities of different possible states are still determined by laws. Thus, there is a difference between the role of chance in quantum mechanics and the unrestricted choices of a lawless universe. Every quantum particle is characterized by a wave function. In 1925, Erwin Schrödinger developed the differential equation which describes the evaluations of those wave functions. By using Schrödinger equation, scientists can find the wave function which solves a particular problem in quantum mechanics. Unfortunately, it is usually impossible to find an exact solution to the equation, so certain assumptions are used in order to obtain an approximate answer for the particular problem. Oregon 2011. The difference between quantum mechanics and Newtonian mechanics is the role of the probability and statistics. While the uncertainty principle means the quantum objects have to be described by probability, this does not mean that the microscopic world fails to conform to deterministic laws. In fact, it does, and measurement is an act by which the measurer and the measured in try to produce to a result. Although this is not simply the determinations of pre-existing property, the quantum descriptions of reality is objective big form, in the sense that everyone armed with a quantum physics education can do the same experiments and come to the world aided by the sum total of all experimental results to be not just a picture of model but identical with the objective or something that exists outside of us and prior to any measurement we might have of it. Quantum physics does not have these characteristics due to its built-in indeterminacy. For centuries, scientists have gotten used to the idea that something like strong objectivity is the हाँ हाँ उठ गया नहीं आटा आटा देने के लिए पीस दे रखे हैं हाँ अब सांझ में the deterministic laws in fact it does measurement is an act by which the measurer and the measured interact to produce a result. Although this is not simply determinations of pre-existing property, the quantum descriptions of reality is objective big form in the sense that everyone around with a quantum physics education can do the same experiments and come to the same conclusion. Strong objectivity it is in classical physics requires the picture of the world yielded by the sum total of experimental results to be not just a picture or model but identical with the objective world, something that exists outside of us and prior to any measurement we might have of it. Quantum physics does not have this characteristic due to its built-in indeterminacy. For centuries, scientists have gotten used to the idea that something like strong objectivity is the foundation of knowledge, so much so that we have come to believe that it is an essential part of the system scientific method, and that without this most solid kind of objectivity, since science would be pointless and arbitrary. However, the Copenhagen interpretations of quantum physics below denies that there is any such thing as a true and unambiguous reality. At the bottom of everything, reality is what you measure it to be, and no more, no matter, no uncomfortable sense. With this viewpoint, quantum physics is extremely accurate, and this is the foundation of modern physics. Perhaps than the objective view of reality is not essential to the conduct of physics, and concepts such as causes and effects survive only as a consequence of the collective behavior of large quantum systems. Oregon 2011. 3.4 The historical origin of uncertainty principle. The origin of uncertainty involve almost as much personality as they do physics. Heidegger's root of uncertainty lies in a debate that began in early 1926 between Heisenberg and his closest colleagues. On the one hand, who exposed the matrix mechanics form of quantum mechanics, and Erwin Schrödinger and his colleagues on the other, who exposed the new wave mechanics. Cassidy 2011. Most physicists were slow to accept matrix mechanics because of this abstract nature and its unfamiliar mathematics. They gladly welcomed Schrödinger's alternative wave mechanics when it appeared in early 1926, since it entailed more familiar concepts and equations, and it is seemed to do away with quantum jumps and discontinuous. French physicist Louis B. Broglie and suggested that not only light but also matter might behave like a wave. Uh, Drawing on this idea, to which Einstein had lent his support, Schrödinger attributed the quantum energies of the electron orbits in the old quantum theory of the atom of the vibration frequencies of electron matter waves around the atom's nucleus. Just as a piano string has a fixed tone, so the electron wave would have a fixed quantum of energy. This led to much easier calculations and more familiar visualizations of automatic events, and than did Heisenberg's matrix mechanics, where the energy wave was found in an abstruse calculation. In May 1926, Schrödinger published a proof the matrix and wave mechanics kept equivalent results. Mathematically, they were the sum theory. He also further superiority of wave mechanics over matrix mechanics. This provoked an angry reaction, especially from Heisenberg, who insisted on the existence of discontinuous quantum jumps rather than a theory based on continuous waves. Heisenberg had just begun his job as Niels Bohr's assistant in Copenhagen. When Schrödinger came to town in October 1926 to debate the alternative theories with Bohr, the intense debates in Copenhagen proved inconclusive. They showed us only that neither interpretations of atomic events could be considered satisfactory. Both sides began searching for a satisfactory physical interpretations of the quantum mechanics equations in line with their own preferences. Classy Day 2011, studying the papers of fellow scientists Dirac and Jordan will the frequent correspondence with Wolfgang Pauli. Heisenberg discovered a problem in the way one could measure basic physical variables appearing in the equations. His analysis showed that uncertainties or imprecisions always turned up if one tried to measure the positions and the momentum of a particle at the same time. Similar uncertainties occurred when measuring the energy and the time variables of the particles simultaneously. The uncertainties of impressions in the measurements were not the fault of the experimenter, said Heisenberg, that inherent in quantum mechanics. Heisenberg presented his discovery and his consequences in a 14-page letter to Pauli in February 1927. The letter evolved into a published paper in which Heisenberg
घालून ना चावल डाल आ ए
हाँ
तू खाला
नहीं नहीं
खाला
मम्मी आई है अभी
हम देखी मम्मी मच्छी ले रही लो ना खा लो
नहीं मैं बाद में खाऊंगी नाश्ता की हूँ
क्यों
नाश्ता की हूँ आंटी
दाल चावल और वो करेला का भाजी
नहीं खाऊंगी
पनीर
मैं
पूरा खा लो ना एक और तू प्लेट में
नहीं
आ नहीं का नहीं खा लो
नहीं नहीं खाऊंगी सही में नहीं खाऊंगी मेरे को भूख लगेगा तो मैं खाऊंगी अभी नहीं खाऊंगी इतना जल्दी नहीं खाऊंगी studying the papers of fellow scientists Dirac and Jordan will frequent correspondence with Wolfgang Pauli. Heisenberg discovered problem in the way of could measure basic physical variables appearing in equation. His analysis showed that uncertainties or impressions always turned up if one tried to measure the position and the momentum of a particle at the same time. Similar uncertainties occurred when measuring the energy of the time variables of the particle simultaneously. The uncertainties or impressions in the measurements were not the fault of the experimenter, said Heisenberg. They were inherent in quantum mechanics. Heisenberg presented his discovery and his consequences in a 14-page letter to Pauli in February 1927. The letter evolved into a published paper in which Heisenberg presented to the world for the first time what became known as the uncertainty principle. Classy Day 2011. 3.5 Some implications of uncertainty. Heisenberg realized that uncertainty relation has profound implications. First, if we accept Heisenberg's argument that every concept has a meaning only in terms of the experiments used to measure it, we must agree that things that can't be measured really have to meaning in physics. Thus, for instance, the path of a particle has no meaning beyond the precision with which it is observed. But the basic assumption of a physics since Newton has been that a real world exists independently of us, regardless of whether or not we observe it. This assumption did not go unchallenged. However, by some philosophers, Heisenberg now argued that such concepts as orbits of electrons do not exist in nature unless and until we observe the Jammer 1974. There were also far-reaching implications for the concept of causality and the determinacy of past or future events that are discussed on the page about the origins of uncertainty. Because of uncertainty, relations are more than just mathematical relations but have profound scientific and philosophical implications. Physicists sometimes speak of the uncertainty principle in the sub-formulations of the law of causality. Heisenberg in 1927 asserted if we know the present exactly, we can calculate the future. It is not the conclusion that we wrong, but the premise. This implies that we can never know the present reality exactly. Heisenberg also drew profound implications for the concept of causality or the determinacy of future events. Even Schrödinger had earlier attempted to offer an interpretation of his formalism in which the electron waves represent the density of charge of the electron in the orbit around the nucleus. Max von, however, showed that the wave functions of Schrödinger's equation does not represent the density of charge of matter. It describes only the probability of finding the electron at a certain point. In other words, quantum mechanics can't give exact results, but only the probabilities for the occurrence of a variety of possible results. Cassidy 2011. Heisenberg took this one step further. He challenged the notions of simple causality in nature, that every determinate cause of nature is followed by the resulting effect transferred to a classical physics. This had meant that the future motion of a particle could be exactly predicated or determined for a knowledge of its present positions and momentum and all of the forces acting upon it. The uncertainty principle denies this, Heisenberg declared, because one can't know of the precise positions and momentum of a particle at a given instant, so its future can't be determined. One can't calculate the precise future motion of a particle, but one range of possibilities for the future motions of the particle. However, the probabilities of each motions and the distributions of many particles following these motions could be calculated exactly from Schrödinger's wave equation. Although Einstein and others object to Heisenberg's and Bohr's views, even Einstein had to admit that they are indeed a logical consequence of quantum mechanics. For Einstein, this saw that quantum mechanics is incomplete. Research has continued to the present on these and proposed alternative interpretations of quantum mechanics. One should note that Heisenberg's uncertainty principle does not say everything is uncertain. Rather, it tells us very exactly where the limits of uncertainty lie when we make measurements of subatomic events. Heisenberg's uncertainty principle constituted as essential component of the broader interpretations of quantum mechanics known as the Copenhagen interpretations. Cassidy 2011. 3.6 Triumph of Copenhagen interpretation. The Copenhagen interpretation is a commonly taught interpretation of quantum mechanics. Classical physics draws a distinction between particles and energy, holding that only the latter exhibit waveform characteristics, whereas quantum mechanics is based on the fact that matter has both wave. The particle aspect postulates that the state of every subatomic particle can be described by a wave function, a mathematical representation used to calculate the probability that the particle, if measured, will be in given location or state of motion. Cassidy, 2011. The Copenhagen interpretation of quantum mechanics is an attempt to explain the results of the experiments and their mathematical formulations as formulated by Bohr, Werner Heisenberg, and others in other years. 1924-27. They theorized a new world of energy quantum entities when fit neither the classical idea of particles nor the classical idea of waves. The hereby stepped beyond the world of empirical experiments and pragmatic predictions of such phenomena as the frequencies of light emitted under various conditions according to their interpretations that act. The measurement causes a calculated set of probabilities to collapse to the value defined by the measurement. This feature of the mathematics is known as a wave function collapse. The Copenhagen interpretation is in form a composite of the statements which can be legitimately made in natural language to complement of statements and predictions made in the language of instrument readings and mathematical operations. Cassidy, 2011. Essentially, it attempts to answer the question, what do these amazing experimental results really mean? The concept that quantum mechanics does not yield an objective description of microscopic reality but deals only with probabilities, and that measurement plays an incredible role is the most significant characteristic of the Copenhagen interpretation, because it consists of these views developed by a number of scientists and philosophers during the second quarter of the 20th century. This is no definitive statement of the Copenhagen interpretation. Thus, various ideas have been associated with it. Some of its key notions are as follows. CI 2011. First, a system is completely described by a wave functions representing an observed subjective knowledge of the system Heisenberg. Second, the descriptions of nature is essentially probabilistic, with the probability of an event related to the square of the amplitude of the wave function related to it. The Born rule after Max Born. Third, it is not possible to know the value of all properties of the system at the same time. Those properties that are not known with precision must be described by probabilities. Heisenberg's uncertainty principle. 4. Matter exhibits a wave-particle duality. An experiment can show the particle-like properties of matter or the wave-like properties in some experiments. Both of these complementary viewpoints must be invoked to explain the results according to the complementarity principle of Niels Bohr. 5. Measuring devices are essentially classical devices and measure only classical properties such as the position and momentum. 6. The quantum mechanical descriptions of large systems will closely approximate the classical descriptions. The correspondence principles of Bohr and Heisenberg regard quantum mechanics as a complete theory for which the fundamental physical and mathematical hypotheses are no longer susceptible of modifications. Heisenberg and Max Born paper delivered to Survey Congress of 1927. 3.7 Difficulties and challenges. No everyone agreed with the new interpretations or with Werner Heisenberg's statements about future work. Einstein and Schrödinger were among the most notable dissenters until the ends of their lives that never fully accepted the Copenhagen doctrine. Einstein was classified with the reliance upon probabilities, but even more fundamentally, he believed that the nature exists independently of the experimenter and the motions of particles and precisely determined. It is the job of the physicist to uncover the laws of nature that govern these motions, which in the end will not require such statistical theories. The fact that quantum mechanics did seem consistent only will not require statistical theories. The fact that quantum mechanics did seem consistent only with statistical results and could not fully describe every motion was for Einstein an indication that quantum mechanics was still incomplete. Alternative interpretations have since been proposed and are now under serious considerations. The objects of Einstein and others, notwithstanding Bohr, Heisenberg, and their colleagues managed to enjoy the acceptance of their interpretations by the majority of physicists at that time. They did this both by presenting the new interpretations on lecture trips around the world and by demonstrating that it worked. The success of the theory naturally attracted many of the best students to institutes such as Heisenberg, some coming from as far away as America, India, and Japan. The bright student nurtured by the Copenhagen doctrine and educated into the new quantum mechanics formed a new dominant generation of physics. Those in Germany and Central Europe carried the new ideas with them as they dispersed around the world during the 1930s and 1940s in the wake of Hitler's rise to power in Germany. Cassidy 2011. Albert Einstein was not happy with the uncertainty principle and he challenged Niels Bohr and Werner Heisenberg with a famous thought experiment. We fill a box that a radioactive material which randomly emits radiations. The box has a shooter which is open and immediately the theater set by a clock at a precise time, thereby allowing some radiation to escape. So the time is already known with precision. We still want to measure the conjugate variable energy. Precisely, Einstein proposed doing this by waving the box before and after equivalence between mass and energy from spatial relativity will allow you to determine precisely how much energy is left in the box. Bohr counted as follows: should energy leave, then the now lighter box will rise slightly on the scale that changes the positions of the clock. Thus the clock divides from our stationary reference frame, and again the spatial relativity. Its measurement of time will be different from ours, leading to some unavoidable margin of error. In fact, a detailed analysis shows that the imprecision is correctly given by Heisenberg's relation within the widely but not universally accepted Copenhagen interpretations of quantum mechanics. The uncertainty principle is taken to mean that on an elementary level the physical universe does not exist in a deterministic form but rather as a collection of probabilities or millions of photons passing through a diffraction slit can be calculated using quantum mechanics, but the exact path of each photon can't be predicted by any known method. The Copenhagen interpretation shows that it can't be predicated by any method. It is this interpretation that Einstein was questioning when he said, "I can't believe that God would choose to play dice with the universe." Bohr, who was one of the authors of the Copenhagen interpretation, responded, "Einstein don't tell God what to do." Einstein was convinced that this interpretations was error. His reasoning was that all previously known probability distributions arose from deterministic events. The distribution of a flipped coin or a rolled dice can be described with a probability distribution 50% heads, 50% tails. But this does not mean that their physical motions are unpredictable. Ordinary mechanics can be used to calculate exactly how each coin will land if the forces acting on it are known, and the heads tails distribution will still line up with the probability distribution give random initial forces. Einstein did not believe that the theory of quantum mechanics was complete, but Heisenberg and Max Born asserted at the famous Solvay Congress of 1927 regarded quantum mechanics as a complete theory for which the fundamental physical and mathematical hypotheses are no longer susceptible of modification. That is the basic difference between them. 3.8 3.8 Philosophical implications of uncertainty principle. The uncertainty principle is often presented as a manifestation of the fact that the act of measurement inevitably betters the state that is being measured. The smaller the particle being observed, the shorter the wavelength of light needed to observe it, and hence the large the energy of this light, and the larger the perturbations is administrations to the particle in the process of measurement. These interpretations will helpful for visualization has its limitation. It implies that the particle being observed does have a precise positions and a precious momentum which we are unable to ascertain because of the clumsiness of the measurement process. However, more correctly, we should view the uncertainty principle as telling us that the concept of positions and the momentum can't consist without some ambiguity, that there is no precise state of momentum and position independent of the act of measurement, as naive religious philosophers had assumed in large everyday situations. This quantum mechanical uncertainty is insignificant for all practical purposes in the subatomic world. It is routinely confirmed by experiment and plays a fundamental role in the stability of matter. Note that if we take the limit in which the quantum aspect aspect of the world is neglected, so Planck's constant H is not set to zero, then the Heisenberg uncertainty would disappear and we would expect to be able to measure the positions and momentum of any object with perfect precision using perfect instruments. Of course, in practice, this is never possible. Barrow 2006. The uncertainty principle has had a major effect upon the philosophy of science and belief in determinism. It means that it is impossible to determine the present state of the world or any small part of it with perfect precision, even through be the profession of the mathematical laws that predict the future from the present with complete accuracy. We would not be able to use them to predict the future. The uncertainty principle introduces an irreducible indeterminacy or graininess in the state of the world below a particular level to observational scrutiny. It is believed that this inevitable level or graininess in the state of matter in the universe during the first moments of its history led to the production of irregularities that eventually evolved in classics. Barrow 2006 experiments are underway in space to test the detailed prediction about the variation left over the temperature of the universe that such a theory makes of the other pairs of physical quantities this Heisenberg sort can be measured simultaneously with arbitrarily high precision. The most frequently discussed pair is energy and time. Strictly this pair is not a true indeterminate pair like position and momentum because time is not unobservable in the way that energy, position and momentum are in quantum mechanics. By using a time defined externally to the system being observed rather than intrinsically by it, it would be possible to beat the requirement that the product of the uncertainty in energy times the uncertainty in time be allows greater than Planck's constant divided by 4 pi. Barrow 2006. The physics Niels Bohr 1885 to 1962 called quantities like position and a momentum whose simultaneous measurement accuracy was limited by an uncertainty principle complementary pairs. The limitations of simultaneously acknowledge of their values is called complementarity. Bohr believed that the principle of complementarity had far wider applicability than Arrhenius deductions in quantum mechanics. This approach has also been adopted in some contemporary religious apologetics, notably by Donald Mackay and Charles Colson. There has also been an interest is using interest is in using quantum uncertainty and the breakdown of risk determinism that it engages to defend the concept of free will and to provide a channel for divine actions in the world in the face unbreakable laws of nature. The uncertainty principle also changes our conceptions of the vacuum. Quantum uncertainty does not allow us to say that a volume of space is empty or contains nothing. Such a statement has no operational meaning. The quantum vacuum is therefore defined. Difficulty is the lowest energy state available to the system locally. This may not characterize the vacuum uniquely, and usually a physical system will have more than one possible vacuum state. Under external change, it may be possible to change from one to another. It is therefore important to distinguish between the non-scientific term nothing and the quantum mechanical conception of nothing when discussing creations out of the in modern cosmology. Barrow 2006.